morning, guys. You're doing okay? Had good breaks, I trust. Well, got a busy week and a half coming up, I know. So I know that a lot of y'all have other exams going on and other assignments. We're in the last final stretch. We have our exam on Monday. Any other big exams going on that day? On Monday? Yeah, what do you have? Calculus 2? You're in 3. Okay. I don't think anybody else is in Calc 3, are you?
I will pray for you.
Yes. So we'll all. Okay. Alright, so we're going to do LR, LC, and LRC circuits. We might not get the phasers and the various AC circuits that we're doing. If we don't, that's okay, because we really only have 2 days. Like we have today and then Wednesday, and then we'll have review on Friday. But this exam is going to cover, most of Chapter 5. We did just the very beginning of Chapter 5 on the previous exam, and then Chapter 6 with, magnetic flux, and now Chapter 7 where we'll do magnetic inductors. All right. Any questions sort of about what's coming up? Exam on Monday, and then our final is like the next week. I think it's usually like the last final. Alrighty. Well, let's look at electromagnetic oscillations. Like I said, we're probably not going to get the AC circuits and phasers, and that's okay. So an inductor is used to create a magnetic field. So an inductor creates a magnetic field, and it does this to help control the current. Because when I create a magnetic field, an inductor will look, it's just a coil of wire basically. And when I send a current through this coil of wire, the current goes around, then I generate this magnetic field in that inductor. And so as I have more and more current going through this inductor, I create more and more magnetic field. But we've seen that when I have a loop of wire like this, and I create this magnetic field because of the current that's flowing through it, then that magnetic field will actually oppose the current. Like we saw that in the previous chapter, that as I have a changing magnetic flux, that the coil of wire will have an electric field induced within it that will oppose the direction or the increase of that changing magnetic flux. And so inductors will control the current in this way through this magnetic field. The symbol that we'll use for an inductor will look a lot like what an inductor is. It's just a coil of wire. So the symbol that you'll see in circuits just looks like that. It's what an inductor is. And in fact, if you've ever looked in circuits, sometimes you might see an actual coil of wire, and that is an inductor. Inductors can also just be, they can be actually encapsulated in a case, but sometimes when you look in circuits, you'll see these coils of wire. The unit for inductance, or the variable rather, is L. We call this L, and the unit is a Henry. I don't know where that comes from, but we abbreviate it as an H, and it has basic SI units of 1 Tesla meter squared over amp. We'll see that because the properties, or the way that we calculate the inductance of a particular inductor, is equal to N, that's the number of turns, does it have 1, 2, 3, 4? How many turns does it have in that inductor? Phi, this is the magnetic flux, and then divided by the current that flows through that. Now we'll see where this comes about in just a bit, why we define our inductance in this way. This, by the way, is called the flux linkage. We're not going to use that term, but if you see these elsewhere and you hear that term, that's where it comes. That's what it's referring to. This is called the flux linkage. The flux, describing the magnetic flux. Let's see, and usually an inductor is considered to be a solenoid. So we've seen inductors already. Usually. right? Because we saw solenoids in the previous couple of chapters, but it's just, as I said, it's just a coil of wire. An inductor is a coil of wire in a circuit. It won't serve the same purpose as a solenoid because we saw solenoids we can use as a switch in particular, but it'll actually control the way the current flows through a circuit. We're going to look at three different circuits: the RL circuit, the RL or the LC circuit, and then we'll look at the RLC circuit. So we'll see different ways that the current flows through these different circuits. So the first is the RL circuit. When current flows, oh, and by the way, the RL circuit will look like this. It'll have a battery, it'll have a resistor, that's my R, and then it'll have an inductor. So that's why it's called an RL circuit, because it has a resistor and an inductor, and then it also has a battery that has an EMF. And so when I hook up this circuit, say it's initially off, and then I turn it on, when I turn it on, the inductor creates an EMF. Right? Remember we said that when we put current through a coil of wire like this, it will actually create an EMF that opposes the current. Like it wants to keep that sort of status quo on what's going on. So it'll create an EMF that opposes the direction of the current. And this was in Faraday's law. Remember Faraday's law, we said that this induced EMF is equal to d phi dt. It's actually negative d phi dt, and we have our n in there as well for our number of turns. Remember Faraday's law? You'll certainly see Faraday's law on the test, so make sure that as you're going through chapter 6 that you're able to use Faraday's law. So as I run a current through that inductor, it changes the magnetic field because it creates a magnetic field, that current going through that wire, and then it generates an EMF within that inductor. So this EMF is going to be opposite the direction of the battery, or opposite the EMF of the battery. So if we think of the EMF going in this direction, that is, it's creating a current that goes in this direction, the inductor will actually create a current that goes in the opposite direction. So the inductor will impede the EMF of the battery as it's sending current through that circuit. And initially the current rises slowly because of the EMF of the inductor. Right, it creates an EMF opposing the EMF of the battery. But after a long time, the current will approach E over R asymptotically. That means it gets really close to it. Well, I'll draw the picture. So the inductor is just a piece of wire. Right? Nothing fancy about it except that it's coiled up into a loop. And initially when I turn on the battery, that inductor will oppose the direction of the EMF. But in order for it to oppose the direction of the EMF, remember Faraday's law, I have to have a changing magnetic flux. But at some point the magnetic flux is no longer going to be changing. It will have increased up to a certain level, but if it's not changing, then the EMF here is going to be zero, because we're not really worried about the flux itself. We're worried about the change of the flux with time. All right? So after a long time, our current will approach a certain value, which is equal to as if the inductor wasn't even there. If I draw this, my current versus time, it's going to look like this. And it's going to asymptotically approach a value that's equal to E over R, which would be a circuit that would just look like this. That would just be a battery and a resistor, as if the inductor's not even there. This is just a piece of wire. It's a piece of wire that's coiled up into a loop, but it's still just a piece of wire. All right? And if the magnetic flux isn't changing, then that loop of wire isn't going to do anything. All right, this should look very similar to you. What was this like? What sort of circuits have we dealt with that had a form that looked like this? The what? Right, the capacitor circuits, the RC circuits, and we'll see the RL circuits. They work identically mathematically, except for different reasons. With the capacitors, we are depositing charges onto those two parallel plates, but now with inductors, we are working with this inductor that's actually opposing the direction of the battery's current, the battery's EMF. All right, so if I have this circuit, then I can write by the loop rule. Let me just draw the circuit again. I have the battery right here. I have a resistor right here, and then I have the inductor. This is L. And so my EMF of the battery, did I write that the EMF is L dphi dt? I'm sorry, I did not. I'm sorry, go back to your previous page. The EMF of this battery, EL, is equal to minus L times di dt. The EMF of the battery is dependent upon the changing magnetic flux, and the changing magnetic flux is dependent upon that changing current. So the EMF of the inductor, this EMF that opposes the direction of the battery's EMF, is dependent upon how that current is changing. All right, so if I go back, and I can write then by the loop rule, I have, let's say that I'm going around this loop, I have a current in this direction, and then let's go around in this direction in the loop, and I have E minus IR minus L di dt. And this is all equal to 0. This is a differential equation. This is a, what order equation is this? Does anybody know? Are y'all NDE yet? Nobody's here yet? No. Well, this is a first order differential equation. You might also call it an ordinary differential equation. That means that it doesn't have a partial derivative. That's as opposed to a partial differential equation. But it's a first order differential equation, and we want to think of a function that will make this equation true. Now some of you will go on to take differential equations, and you'll sort of go through the process of solving these and figuring out what is the function that will actually make this equation true. We're not going to do that so much here, but we're going to, in fact, you'll have a take-home portion. I'll give you what the solution is, and then I'll want you to show me that that solution does satisfy this equation. It's really just doing derivatives, but I'll give that to you as a take-home, and I'll show you what that is today, your take-home that'll be due next Monday. So I have this equation, and I want to find a function for I. Notice I have I here, and I have di dt here. I want to find a function for I that will make this equation equal to 0. Now, the function that makes this equal to 0 is this. It's going to be I is equal to E over R times 1 minus e to the minus RT over L. I'll show you how that works, and we'll plug that into that differential equation and show that it does in fact solve that equation and make it all equal to 0. I can simplify it a little bit. I can say that tau, remember we had a time constant for our RC circuits. We're going to have a time constant as well here for our inductor circuits, our LR circuits. Tau L is going to be equal to L over R. This is our inductive time constant. Just like we saw for RC circuits, it's in units of seconds. All the same stuff that we saw for RC circuits apply, that it is 1/10 of the total time to charge our circuit for our current to reach its maximum value. So if I do that, then I can rewrite this. I get I is equal to E over R times 1 minus e to the minus t over tau L, just like we had for RC circuits. And notice that this current, it looks like, if you recall, that if I write my current versus time, just like we had for RC circuits, this is a exponential growth function. That means it's going to look like this. It will approach asymptotically a certain current, and that current will be equal to this value, which is E over R, which is just from our Ohm's law, right? V is equal to IR, so my I is my EMF over the resistance. All right? Let's show that this is true. So beginning with my loop rule, I have E minus IR minus L di dt equal to 0. You'll do a similar thing for your take-home, but it's going to be a second-order equation instead of a first-order. So I have E minus I times R. Well, I is going to be E over R times 1 minus e to the minus t over tau L. So that is I. All I've done is I've just plugged this in there, times R, minus L times di dt. Now remember that if I'm taking the derivative of an exponential function, the derivative of e to the minus rt over L, that this is equal to minus r over L times e to the minus rt over L. Y'all seen derivatives of exponential functions before. You should have. We haven't done them in this class, but you should have seen them in Calc 1. But when I take the derivative of this exponential function, all I do is I take the derivative of the exponent with respect to t, which is going to be just minus r over L, and I pull that out, and then the exponential function just stays the same, the exponential part of that derivative. All right? So that's how I find the derivative of that. Now, if I apply that over here, I get the derivative of I with respect to t is going to be L times E over R times R over L times e to the minus RT over L. And then that's all equal to 0, supposedly, if our solution is correct. Now let's see what I've done here is I've taken the derivative of this thing. The derivative of 1 is 0. The derivative of negative RT over L, which is what this is, this minus t over tau, is equal to this thing right here, this R over L, e to the minus RT over L. Notice also that I lost a negative sign along the way. I lost this negative sign because when I took the derivative of this, this becomes our coefficient, and the two negatives cancel one another out. All right? Don't sweat this too much. You're not going to have to do this on the next test, but you will have to do it on the take-home. So sort of look at how we're doing this. But in short, all I'm doing is just plugging in the solution for I, taking the derivative of it, and now I want to show that this is equal to 0. So I'm sorry, I should have a positive here. Hold on, guys. Let's see. I lost a E somewhere. Oh, no, I didn't. This is not a positive. Okay, so now I want to go through. I can do some cancellations here. I can get rid of the R there, and so I get E minus E minus e to the times the exponential of negative t over tau minus, let's see, my r's cancel there and there, my L cancels here and here, and so I'm just left with minus let's see, I should have a positive E. Oh, wait, no, this one's positive right here. Minus E to the E minus RT over L. And then that's all equal to 0. All right, so I get these two cancel out, and I get these two cancel out. So this solution for I does solve that first order differential equation. Okay? Y'all follow me on this? If you're not following the details of this, that's okay. But in short, I'll give you the assignment later in just a little bit. But I'm going to give you a second order differential equation, which just means that you'll have not one derivative, but you'll have a second derivative that you'll have to take. And I'll give you the solution, and then I'll ask you to solve that and show that it's correct. Okay? All right. So similar to capacitors, when the EMF is off, the current decays exponentially. So this graph that I show up here, this is when the current is on. That's just like it was for capacitors. The function looks exactly the same. In fact, this looks the same, and then the graph looks the same as well. And so when I have it off, my function looks like this. I, t, looks like that. It's an exponential decay function. The maximum current here is E over R. And my current then will be E over R times e to the minus t over tau. So these work mathematically identical to RC circuits. They just work for a different reason. And the reason here that I get this, if I turn off the battery, if I turn off the current, I turn off the battery, and I'm left just with a circuit that looks like this, where I have a resistor and an inductor. I get this decay because all of a sudden you take out the battery and the current, the source of the current goes away, but the inductor is going to oppose any change in magnetic flux. And when the current decreases, that changes the magnetic flux. So now the inductor is going to actually provide an EMF that's in the opposite direction of the decaying or the declining current, which will actually cause the current to decline more slowly. All right, so both of these expressions are on your equation sheet. Make sure that you're aware of that. There are a number of different expressions on that equation sheet. So make sure you're aware, be able to calculate the current at a particular time, very much like we did for our RC circuits, be able to draw what the functions look like, and then also be able to describe why it is that that happens, because this inductor is opposing any change in the magnetic flux. All right, let's talk about the energy that's stored in a magnetic field. And that's sort of, oh, no, I think first we have an example. So let's say I have a circuit that looks like this. It is an RL circuit. There's my resistor. There's my inductor. The inductor is 53 millihenries, and the resistor is 0.37 ohms. And I want to know, how long does it take to reach 1/2 the equilibrium current? Well, I know that the equilibrium current is going to be equal to the EMF over the resistance. And I don't know what the EMF is. It doesn't really matter because I don't want to know what is the equilibrium current or what is 1/2 the equilibrium current. I just want to know how long does it take to reach that. And so my equilibrium current, just from Ohm's law, is equal to E over R, the EMF over R. And then I know that my current at any particular time, I as a function of t, is equal to E over R times 1 minus e to the minus RT over L. All right, so now I want to say, well, my equilibrium current is going to be E over 2R. That's just because I'm looking for 1/2 the equilibrium current. Right, and that is 1/2 the equilibrium current. is equal to E over R times 1 minus e to the minus RT over L. Alrighty? Remember how to solve for functions when you have these exponentials in them? We're going to do it on the previous test, I think. That will make us solve for t. Yeah, so you have to use the natural log function on your calculator to get rid of that exponential. I can do some cancellations here. I get my e over r's cancel out, and I'm left with 1/2 equals 1 minus e to the minus RT over L. This is negative 1/2, because I bring this over, I subtract it from both sides, equals negative e to the minus RT over L. This becomes positive, and then I take the natural log of both sides. And when I do that, it gets rid of that exponential, and I get the natural log of 1/2 equals minus RT over L. And now it's pretty easy to go from here to finding what is the time. I'm going to call this T 1/2 because it's the time for half the equilibrium current to occur. And so T 1/2 is going to be negative natural log of 1/2 times L over R. L is 53 times 10 to the minus 3. And R is 0.37. All right, so that's going to be I get negative 0.69 for the natural log of 1/2, and I lose the negative. I get 0.099, I think that's right. Yep, so we'll just call it 0.1. 0.1 seconds. All right, so that is half the time to reach my equilibrium current. Our time, rather, to reach half the equilibrium current. So if I'm looking, remember, at my current versus time, it looks something like this. If I want to know the total time to reach the equilibrium current, I'll call this T tot. It's going to be equal to 10 times tau L. So 10 times L over R. Which in this case is going to be, well, L is 53 times 10 to the minus 3. L is 0.37. Tau L is 0.14. And so 10 times that is going to be 1.4 seconds. So this is 1.4 seconds. All right, that's not new. It's exactly like what we did for RC circuits. The time to reach the total current is 10 times the time constant. And then if we're looking for half the current, that's like right here, it's going to be about, well, about 1/10 of that. Or not quite 1/10. It reaches that half current really quickly is the point. So my half current, which is right about here, occurs at about 0.1 seconds. All right? You should be prepared to do that. You have the equation. Just make sure that you know how to do solving the equation and dealing with these exponential growth and decay functions. Y'all can do that okay? I think many of you could probably go into it today, but if you're having trouble with it, make sure that you master it. There's homework problems to help you practice. And if you look back at the old tests too, you'll see some similar problems. But come see me if you have trouble with those exponentials. I can absolutely help you. All right. Y'all look excited about this. Are you really excited? Yeah, I know these circuits are kind of dry. They are kind of dry. They're certainly not as exciting as other stuff that we've done the rest of the semester. But it's useful for you to learn to deal with these, with the exponential functions and also with the differential equations. Many of you will actually go on and take those classes and see sort of how they work. All right, let's look at energy stored in a magnetic field. We're still going to do LRC circuits, and we'll look at how they transfer energy back and forth to one another. Actually, we're going to look at LC circuits here. So electric charges store energy in an electric field. we've sort of seen this, right? When you think about, I have positive charges over here, negative charges over here, say in a capacitor, that's what a capacitor is, and there is an electric field that goes between them, and there's energy in that electric field. I know there's energy because if I take a charge and I put it, say, right here, it's going to move in that direction. So there is energy stored in this electric field. And so when I have electric charges, I can think of them storing energy in their electric field. So electric charges store energy in an electric field. And in a similar way, oh, and by the way, we saw this with capacitors, right? In capacitors, we talked about how they store energy. We said that energy was equal to 1/2 CV squared, or 1/2, what was it? I think it was Q squared over C. We had several expressions for the energy in a capacitor, and we'll see that again when we deal with LR circuits. So in a similar way, magnetic fields can store energy. And the magnetic field is equal to, we're going to call this UB, is equal to 1/2 Li squared. And so just sort of keep the same notation, we'll say that the energy stored in an electric field, which we'll call UE, is equal to this 1/2 Q squared over C. This is the energy stored in a capacitor. And this is the energy stored in an inductor. All right, I can have energy in a capacitor and I can have energy in a conductor. The energy in an inductor is stored within the magnetic field, and it's equal to this value. We're not going to derive this, but just know this is our energy stored in an inductor due to the magnetic field. Excuse me. And this is the energy stored in a capacitor due to the electric field. What we're going to see with RL circuits, or with LC circuits, excuse me, is that the inductor will store energy and the capacitor will store energy, and they're going to trade it back and forth, kind of like a kid on a swing. All right, so let's look at that, where an LC circuit will look like this. I'll have an inductor, and I'll have a capacitor. Notice there's no battery in this, so I'm assuming here that at some point either my capacitor or my inductor is charged up, is given energy, and then we walk away from it and allow the LC circuit to just operate. So LC circuits in this case, the charge, that's the charge on the capacitor. The current, that's the current through the circuit. There will be a current, at least, we'll actually talk about the current being in the inductor. There is no current through a capacitor, but when charges are discharged from a capacitor, they can send a current between the two sides. There is no current through a capacitor because it's just parallel plates, so nothing passes in between those. All right, so Q, I, and the change in potential, they'll all vary sinusoidally. Right, they'll vary like this, like a sine curve. And as I said, the energy of the capacitor, that's UE, is 1/2 Q squared over C. So when there's a certain charge on the capacitor, it holds that energy. The energy on the inductor, which I'll call UB, for the magnetic field, is 1/2 Li squared. Notice that the energy on the inductor is most when the current is biggest, because that's when you have your current is changing the most amount. and it's going to have a maximum changing magnetic flux. So I'll have the most energy here. The energy in my capacitor is most when I have the most charge on the capacitor. What happens to my current when all of my charges are on my capacitor? What happens to the current in the circuit when the capacitor is fully charged? Now in this circuit I only have a set number of charges. And what happens then to the current if all of those charges are on the capacitor? My current goes to zero, right? Because all the charges are on that capacitor. They're not out moving around the circuit. What is the charge on the capacitor when the current is at its maximum? What is the charge on the capacitor when the current is at its maximum? It's also zero, because you can think about all those charges are out moving around in the circuit, and there are no charges on the capacitor, so that means I have maximum current. And so we can think about the energy being transferred between the inductor and the capacitor. When I have maximum charge on the capacitor, I have no current. So when I have maximum charge on the capacitor, I have maximum energy on the capacitor, but I have no magnetic energy. And when I have maximum current in the inductor, I have no charge on the capacitor, so all my energy is in the inductor. All right, so you can think of it sort of like this. Let's say that we have a circuit. It's an LC circuit. Initially, my capacitor is fully charged, so I have all my charges over here. So UE is at its maximum value. There is no current, because all those charges are on the capacitor, and I have a magnetic energy that's equal to zero. So there's zero energy in that inductor because there is no current. All those charges are on the capacitor. Then, as those charges begin to move through the circuit, let's say that I just lost half my charges. So here I have total charge. All the charges are on the circuit. Here I have, say, half the charges on the circuit, but the other charges are out moving through the inductor. So here I have a current that's flowing through the inductor, and then I also have a magnetic field. My magnetic field here, because I have a changing current moving through that inductor, I have a magnetic field. So here I have UE, the magnetic, or the energy of the electric field, and here I have the energy of the magnetic field. Now in this case, UE will equal to UB. All right, then I can get a point where I have no charge on the capacitor. So I have Q equals 0. That means that UE will equal to 0. It'll be at its lowest amount. I'll have a maximum current. And then over here, I have maximum UB. Now what you're going to get is you're going to get this thing that's going to oscillate back and forth between these states. Here I'm going to have a stronger magnetic field. In fact, the strongest magnetic field that I have will be at that point when the charge on the capacitor is equal to 0. All right, and then we can go back. So then we get a capacitor that will look like this, but now it's actually going to change direction. So whereas over here I had negative charges, and here, now I'm going to actually get positive charges here and negative charges here. My currents now, instead of going in one direction, will actually go in the other direction. So now my current is going to look like this. I will have a magnetic field over here. It's going to be opposite the direction that it was before. I'll have an electric field energy, and I'll have a magnetic field energy, and that UE will equal to UB. And then I'll come back to this stage where I have maximum electric field energy, no magnetic field energy, no magnetic field. All right. if I look at my plots for Q and V, they're going to look like this. So this is Q and the voltage across the capacitor. And remember, these are equal to one another, or they're related, because Q is equal to CV for our capacitors. It's going to look like this. It's going to start up here, and it's going to go down like this. So if I'm looking at, say, this, if I call this point A, this will be point A on the graph, because I have maximum charge, maximum potential on my capacitor. What is, say, at this point? Well, let's label these four figures. I have A, B, C, and D. What is, say, this point right here? Is it A, B, C, or D? Let's do it as a clicker question. I want to know, what is this point? Given these four circuits, what is this point right here? Is it A, B, C, or D? What does this graph show as a function of time? This graph shows what? It shows the charge on the capacitor. And then it also shows, because they're equal to one another, they're related to one another, they're proportional, it also shows the voltage on the capacitor. Likewise, it's also going to show the energy in the electric field, which is the energy of the capacitor. So I want to know which of these scenarios has this amount of charge or this voltage on the capacitor. Now here, the charge was at its maximum value. I have maximum charge on the capacitor, which is right here, maximum charge. I have no current because all the charges are on the capacitor. I have no magnetic energy because there is no current. I have to have a changing current in order to have a magnetic field there. And so here I want to know, what point does this represent in these four circuits? Is it A, B, C, or D? What is the charge at this point? What value is it equal to? It's equal to 0, right. So I want to know which circuit has that scenario at that point. Okay, awesome. That's a lot better. So let's stop at 142. Okay, good. C is right. So at this point, my charge is equal to 0. And so that's going to be this circuit right here. Now, B, most of you had B up before. It's sort of flip-flopped. B would be like right here. So this was B. This is C. And then D is going to be like right here. Notice that my current has changed direction now. That it was going one direction, but now it's going the opposite direction. That's because the charges are going a different direction. All right, so my Q looks like that. If I look at my current, it's going to look like this. This is going to be the current through the inductor, and it is a similar, or this is a cosine function instead of a sine function, so it's shifted in phase by 90 degrees. So notice here, initially, no current. This point has maximum current. Which of these would this be? This is going to be C, right? Because it has my maximum current. And then this down here would be, let's see, I didn't draw that one, but it's going to be where I have maximum current, but in the opposite direction. So let's sort of label some of these. This is going to be point A right here. This is going to be C right here. B is going to be right here, and then D right here. Actually, D didn't change current. Actually, I would say that's D. That's okay. All right. Let's look at, often we use like an idea of an oscillating spring.
You can think of it as an oscillating spring because when I have a mass on a spring, I have two types of energy. I have the energy of the spring, and then I also have the kinetic energy of the block. And so we can sort of think of our inductor circuit, this LC circuit, as changing off between potential energy and kinetic energy. And the potential energy being the energy of the capacitor, and the kinetic energy being the energy of the inductor, because it's dependent upon charges actually traveling through it. And so if I think about my circuit, I have this LC circuit. I have maximum charges over here. I have no current. I have no magnetic energy, UB equal to 0. I can think of this as it having maximum potential energy. So if this is my equilibrium position, it's like I have this spring that is fully stretched out. And so all of my energy is wrapped up in this capacitor. Just like here, all of my energy is wrapped up in this spring. Then I can go on to where I have no charge, Q equal to 0, maximum current, and here UB is at its maximum value. And this would be like sort of thinking in this analogy of the block being where? Would the block be over here, right here, or would it be over here? Sort of thinking about this analogy, where would it be? Would it be to the left at the equilibrium position or to the right of the equilibrium position? To the what? Are you guessing? What do y'all think? Are you guessing? No? Okay, it's going to be at the equilibrium. It's a good guess, but I'm going to have it at the equilibrium position. Right here, because here, I have maximum current. Here I have maximum velocity. So I have maximum kinetic energy of the block. I can go on. My third scenario, where I now have charges that are, the capacitor is fully charged, but notice that they're on opposite sides of the capacitor. My current is 0. And this is going to be like the scenario where my block is to the left of the equilibrium position. V is equal to 0 here. So my potential energy is at its maximum value at that point. All right. This is sort of the same idea as what we've had before, but I'm just switching back and forth between the potential energy in the electric field and the potential energy in the magnetic field. I want you to have an understanding of how these LC circuits operate, that they swap energy back and forth, and then also be able to calculate what that energy is. And we'll get into that next time, I think. Let me just give you I'm going to give you the loop rule for this. And next time I'll give you the second order ordinary differential equation, or we'll solve that, or I'm going to give you the solution, and then that's going to be your take home. So my loop rule looks like this. I have delta V of the capacitor plus delta V of the inductor. That's equal to 0. And so delta V of the capacitor, that's just Q over C. That's from our Q equals CV. But delta V of the inductor is going to be minus L di dt. That is the EMF of the inductor, and it's going to be opposite the EMF of the capacitor. And this is equal to 0. All right. And notice here that I have a variable Q and a variable I. They're related to one another, but they're different. And so I want to get these all in terms of Q. Now I is equal to dq dt. Actually, I'm going to start using lowercase q. dq dt. And so I can rewrite this as q over c minus d squared q dt squared. And that's equal to 0. So this is my second order differential equation. It's a second order because I have a second derivative here instead of a first derivative like I had in the previous one. So what I want to do is figure out a solution for q that will give me this equation to be 0. And I'm going to go and give you the solution. What's that? Did I drop an L? Oh, yeah. Okay, so now I can rewrite this as d squared q dt squared is equal to minus 1 over LC times q. And the solution that we're going to have for this is, actually we'll wait and I'll give you that next time, where when I'm going to give you the solution, because this is going to be your take home, q is going to equal to maximum q cosine of omega t, where omega is equal to the square root of 1 over LC. So your take home, which I'll put it on Moodle sometime soon, your take home is going to be show that this solution solves this equation. All right, so what you're going to do is you're going to take this solution, taking omega to be this 1 over root of 1 over LC, and plug it in here and here to show that these two sides are equal. If you look around the internet, you might be able to find the solution, but just it's doing the derivatives of your sines, your sines and your cosines. So it's certainly something I think that you're capable of doing. But if you have trouble with it, let me know. I'll send this out as a more formalized take-home question, but it'll be 10 or 15 points on your exam 4 coming up on Monday. All right. I don't mean to give you more work, but it'll make your exam a little easier. All right, guys. Y'all have a great day. I'll see you Wednesday. We're going to wrap this up on Wednesday. We're not going to get to alternating current, but we will do, we're going to skip over those 3 circuits in alternating current and phasors, but we will do transformers. We'll skip ahead a bit. Y'all have a great day. Welcome back. I did.